Exoplanets. What is an exoplanet? It's a planet orbiting another star system other than our own sun. So it would be outside of our own planetary system or solar system. Though the planet size would be so relatively low to detect, a clever method was introduced to identify the existence of an exoplanet, which is by noticing the dimming of the star flux as the planet orbiting passes in front of it, and it blocks partially a part of the flux being emitted by this star. So as it passes in front of the star in the direction of the astronomical device observing that star, the partial blockage of the flux would be detected and measured, and from that we can actually get the radius of the planet orbiting this star, its velocity, different dimensions like the radius, the velocity, even its distance from the star itself. Okay, it would be a little bit complicated, but it's interesting how we can, from the blockage, the partial blockage of the flux of the star, detect the existence of an exoplanet. So how do we determine the area of the planet relative to the area of the star it's orbiting? The ratio of the flux that has been blocked by the planet to the full flux is directly relative to the ratio of the area of the planet in respect of the area of the star it's orbiting. In other words, delta F, which is the change or shift of the flux in relation to the full flux of the star, or delta F over F, is equal to the area of the planet divided by the area of the star it's orbiting. In this illustration, you notice that the brightness of the star had dimmed, okay, had dropped a certain degree. So what would that delta F be equal to? If you have a chart like this, where a brightness is measured like 1, 2, 3, 4, for example. So the brightness had dimmed, let's say, by 10%. Okay, so delta F, which is the original brightness, let's say it is 4 here, okay? Minus the actual brightness when this planet had come in front of the star, blocking partially its flux. So the flux when the star comes in front of this, when the planet comes before this star, is equal to 3. So 4 minus 3 divided by 4, okay, which is equal to 1 over 4, or 25%. Okay, 25%, or 0.25. This is equal to the area of the planet, the ratio of the area of the planet divided by the area of the star, which is 4 pi r squared, by the way. It is the area of the sphere entirely, but from that you can get the radius as well, the radius of the planet. So from the area ratio, we can get the radius of the planet relative to that of the star also. Delta F over F is equal to 4 pi r squared P divided by 4 pi r squared S. 4 is deducted here, it is removed, because you can factor it out from the numerator and the denominator, but don't forget, we have a 4. It's the area of the sphere, not the area of the disk section that is visible to you. It's the entire sphere. Okay, so this gives us Rp squared divided by Rs squared. Rp is radius of the planet divided by the radius of the star. So delta F over F is equal to Rp over Rs squared. Now, how do we measure the period of rotation, or the period of one cycle for the planet around that star? By measuring the time span between two passages of the planet, which is the time distance from the beginning of the first dip, like in here, in brightness, to the beginning of the second or next dip, we can find the rotation period of the cycle. That would be the rotation period. And you'd start to measure it. It might be days, it might be, I don't know, okay? It requires patience and measurement for long periods when it comes to exoplanets. Given we calculated the mass of the star, how to measure the orbital distance from the core of the planet to the star, and then the orbital velocity. The orbit here in this peculiar case is considered circular. For the orbital velocity, the gravitational force, F gravitational, is equal to F centrifugal when it comes to a circular orbit around a sun or a star. Okay, so the gravitational force is given by G lowercase m capital M divided by r square is equal to m lowercase m v square divided by r, whose lowercase m of course is the mass of the planet orbiting the star. Capital M is that of the star itself. So the velocity, which is a constant in such case, because you have a circular orbit, so it's a uniform velocity, constant speed with no acceleration. So V0 is equal to square root of gm over r. That would be the tangential velocity of the planet around the star. The rotation period, okay, so this is given by the simple formula. When you have a constant velocity, the distance traveled by an object is equal to the velocity of that object multiplied by the time. Here you have a uniform velocity but in a circular orbit. So distance traveled, which is 2 pi r, or the circumference around the star, correct, with r is the radius of rotation, is equal to v0, velocity traveling around this star, multiplied by the period, which is the time it takes for one cycle, one full rotation. So P is equal to 2 pi r divided by v0. P is equal to 2 pi r divided by square root of gm over r, because v0 is equal to square root of gm over r. We just calculated that. Mind you that the gravitational constant g is given by 6.67430 multiplied by 10 to the power of minus 11 meter cubed, kilogram minus 1 times s minus 2. So we raise up the power of the period in order to get rid of the square root. So you get p square is equal to 4 pi square r square divided by gm over r. R is lifted up to the numerator, so we end up with p square is equal to 4 times pi square times r to the power of 3 divided by gm. This is how we get the period of rotation of the planet around the star.